I want to thank everybody for joining us here for the April MIDAS webinar. My name is Harry Hockheiser. I'm the director of the MIDAS Center. And it's my pleasure to host these webinars and to introduce our guests. We have lately been encouraging trainees, pre-doctoral and postdoctoral folks to come and present their work as they go. And speaking only for myself, I think I've found that to be really very interesting. And we've already seen some nice talks along those lines. And so we're going to continue in that model today with Gursharn Kaur. Dr. Kaur is a postdoc at the Biocomplexity Institute at the University of Virginia, where they've got a very strong group of modelers who we've worked with through MIDAS. Dr. Kaur has a PhD in statistics from the Indian Statistical Institute. She's previously had a postdoctoral fellowship at the National Institute of Singapore before coming to Virginia. Her interests lie in epidemiological modeling and forecasting, reinforcement models on network subgraphs, enlarged random networks, and analyzing different tree shapes for random phylogenetic trees. So today she's going to talk about something that is really, I think, a key topic in modeling as we see the importance of groups like the forecast hubs and these other efforts that have built large communities of people to tackle similar problems. So this question of ensembling techniques for these probabilistic forecasts is an important one, and I'm looking forward to hearing what Dr. Kaur has to say to us today. So with that, I'll hand it off. Looking forward to your talk.
Okay, thank you so much, Harry and Kristen, both, for organizing this. And any point of time, please feel free to stop. And if you have any questions, and I feel you can stop, write the message or questions in the chat box. Okay, so I'll talk about the ensemble techniques that we have looked at it for the probabilistic forecast specifically. And this is a joint work. Why cannot now? Let me see. Yeah, so this is a joint work with my team at the Biocomplexity Institute, where we have Aniruddha, Ben, Lijing, Shemek, Srini, Brian, and Madhav. And this project was funded by several agencies, including NSF, CDC, CST, VDH. So what is an ensemble problem that we are looking at? So let's say we have a time series. So this is a very simple example of epidemic time series I've taken. Just a simple, nothing specifically to COVID or anything, but so let's say we have a time series with some data points, and there are two different models giving us forecast for next 4 weeks. So here you see this red line as a, let's say, ground truth time series, and for the next 4 points, we have 4 forecasts with their uncertainties. So that could be 90%, 95% confidence intervals from these two models. Now, the problem that ensemble problem we are looking at is how do you effectively combine these probability forecast for these 4 forecast time points. So why ensemble techniques? So the ensemble techniques, they combine the forecast from different models. And there could be 2 different types of ensemble techniques. One is parametric and the other is non-parametric. So with parametric method is the one where we assume some distribution given by the we put a distributional assumption on a forecast given by any model. And the non-parametric is where we don't assume any distribution, but we put some weights and take some sort of weighted combination of these individual forecasts. So these forecasts could be in terms of probabilities, or at specific levels we have quantiles. So it could be at the level specific, you can look at the weighted quantiles, weighted average of these quantiles. And some simple examples of these non-parametric methods is a mean ensemble, where you take simple mean of all the, let's say you have 95% confidence interval with a median, then you can take from different models, then you can take a simple mean of all the lower bounds, all the upper bounds, and all the medians. And the other example is the median ensemble, where we look at, so you fix the lower bound of that interval, and then look at the median of all the lower bounds. That's median ensemble lower bound. Median of all the median forecast, so that would be a median forecast for the ensemble, and so on. So we'll look at both of these. And which one do we choose? That depends on the problem and whether we can actually make some distributional assumptions or not, whether the model has a forecast that is given by some distribution. So if there is some net model property that tells you that there is a forecast does have a distribution, then we can utilize that and make a parametric ensemble. So the benefits of ensemble methods is it reduces individual model bias. So there could be some models capturing some sort of aspect of the time series or the epidemic, some properties. And if we only focus on one model, we might be looking at something important, but the other model could be looking at something other, some other important aspect of the epidemic time series. So in order to combine these two and to avoid these specific model biases, we look at this ensemble and aggregate these forecasts. And it also gives you a better uncertainty estimation by combining all the different sources of uncertainty. So different models can capture different sources of uncertainties. So that's a better way of, so to give an overall uncertainty estimation from the ensemble from any of these two models is better than looking at any individual model. So let's first look at the parametric ensemble approach. So the first one we look at is the Bayesian model averaging. So I'll briefly describe what the Bayesian model averaging is. So let's say we have m different models. We consider them as independent models. So we don't know. So we assume that none of the models interact with each other. They are giving forecasts independently. Let's say this capital M denote a model and the index denotes the just a model index, which model it is. So there are small m many models, and they are all targeting time series Y based on the historic data YT. Then the joint distribution here can be written as the weighted sum of these at the target variable Y given the model MI and the historic time series, historic data, and the weight that the model gets based on this. So this can be interpreted as the probability that the model MI is the best model among the set of M models here. So that's the weight, and this definition holds by just the total probability law. And here WI can also be interpreted as as I said, the posterior probability that model MI is the best model among the set of all M models. So you can also think of it as there's a latent variable which takes value 1 if the model at place I for model I, if the model I is the best model. Now these WIs are the probabilities, so they should sum up to 1. So these are the model weights for this Bayesian approach. Now let's say we look at just an example. Let's say we have this Gaussian distribution. So let's say every model is giving the forecast for Y in terms of some Gaussian distribution with mean mu I and variance sigma I square. Then the Bayesian ensemble will have, so this sort of ensemble with weights WI will have mean summation, the weighted mean for the given, with the given means from the individual models and the variances. And this holds because of the independence property here. But the weights, now if you want to get the optimal weights, so the problem here is that we want to get the optimal weights, we need this, you consider these WIs to be as parameters. And we get these parameter estimates from their MLE or maximum likelihood estimates using the training data. Now the problem here is with the Gaussian distribution is that there is no closed form solution for these MLE estimates. So, but there are other methods to get such estimates. For instance, one is EM algorithm, expectation maximization algorithm. So for this, you define a latent variable Zi, which is an unobserved variable, which denotes 1 if model MI is the best model and 0 otherwise. So then the expectation maximization step involves the computation of these two. So you start with some initial weights and then compute this conditional ratio of this two probabilities, weighted probabilities. And then next step, we update these weights based on this updated latent, this variable Zi's. So average of these over time and the sigma square. So not going much into this EM step details. So there's a way to compute overall, get the estimate for this model parameters. So you keep iterating this until the WIs have converged to one number here. So in our earlier work, what we did is from the University of Virginia, we were one of the teams submitting forecasts for more than 2 years to COVID-19 Forecast Hub. And the COVID-19 Forecast Hub in the US is maintaining the COVID-19 forecast at the county level. And so the UVA Forecast Hub model was an ensemble model, which consisted multiple models, which some of these were statistical models, some were machine learning models, some were mechanistic models. And then we were using this, we were running all this set of models and then getting one ensemble, and that ensemble was the Bayesian model averaging ensemble method. So we have been submitting these ensembles for since 2020, and this so the forecast submission was done every week at the county level. So it was a really extensive process. It was running several models at a county level for more than 3,000 counties, and for every week for 4-week ahead forecast. And the work by one of our team members by our team showed that instead of using one single model, it's always best to use a combination of these different models because they capture different properties of the epidemic. And it's so that work said that all models are useful and the Bayesian modeling is much robust than any single model here. Now, from this work, when I joined, we started looking at how we can improve such an ensemble model. So some of the key observations we made to improve such a model is we looked at this COVID-19 time series specifically, and we observed that it goes through 3 different phases. As like any other epidemic time series, COVID-19 also goes through different phases like growth, rapid growth, surge, plateau, and decline. But the important point here we noticed was that the specific model performed better during certain phases. So depending on which phase we are currently in, the different model performance changes over time. So, and the next observation was that this specifically during the surge phase, the ensemble may not perform really well. And that this could suffer because of the sudden change in the phase and sudden model performance change. And we also observed that such thing is happening with the bigger set of, so all our experiments are with our set of models, this set of models that I described. But this is true, such an observation holds even with the set of forecast submodels, where we have like not hundreds, but dozens of models. Like I think there are more than 35 models there. So what we proposed here is the first step is the phase identification. There should be a robust way of identifying these phases, or change points that we identify these important phases. And then we should be able to see that this performance varies between these phases. So these phases should actually capture this performance over time for the models. And then after identifying these phases, we updated our model averaging technique, our Bayesian model averaging, using this phase identification method, phase of the pandemic. And then we also evaluate and see whether this proposed solution does better than the standard Bayesian model averaging or not. So coming to the first contribution, we we developed a method to identify these phases. It's a very simple method. So you take a time series. So this is a time series for US over the time period. We take this time series and then we approximate it with a piecewise linear time series. So here, all these red stars, between any two red stars, it's a linear function. Then, so we find such a approximation, and then between any two red dots, or we call the breakpoints, where the linear structure changes, we say that the time points between these two consecutive red stars, breakpoints, is in surge, decline, or plateau based on how much change was there from the start of the this breakpoint to the end of this linear fit. If there was at least 10% increment, we called it a surge phase. If there was at least 10% reduction, so for instance, here we see that there was at least 10% reduction from here to here, we call it a surge phase. From here to here, again, it's a surge phase. But from here to here, it's a decline phase because there is at least 10% reduction. And for if it's not a reduction or increment, then we call it a plateau phase. And how do we get this? We use this R package segmented to fit a better, piecewise linear fit with a given nonlinear time series. And then after we identify these phases, let's say now we have this phase Y1, phase Y2. Let's say that denotes the phase of the time series at any given time point T. Then we update the posterior distribution of that described earlier. So we update the posterior distribution of the ensemble using these estimated phases. So now we utilize this phase information in the posterior distribution. So here again, we have the similar setup, the Bayesian model averaging, that where we have these where we use these as model weights we were estimating. But now where we update our training data, as we only take the previous time points, so from the historic time point, we only take times ys, where the phase matches exactly with the forecast time point. So if we are at time yt, at time t, we know what the phase is. And then we go back, let's say if it was surge, then we go back and see that where all it was in the surge phase. So we only take that as a training data, and then so restrict that training data to that specific phase. So then the model weights, and then again, we use the EM algorithm to obtain our model weights. So that's the same process, but just the BMA, but with a restricted training period. Then we evaluate our model. So we observe that our PI BMA is a phase-informed BMA that assigns higher weights to the model with better performance during the similar phase, because that's obvious, because we are restricting to a similar phase. It would be doing a better performance during the similar phase. Now, for example, here, the one interesting thing we saw here is that, so here, if you see, the BMA is the blue line, and the remaining colors are the dot in the dotted lines, and the shaded region denote their uncertainties. They're 95% confidence intervals. And the red one denotes the BMA with a phase-informed. So here we observe that when the phase started changing, and as soon as we started entering a different phase, it started entering in decline or plateau. It learns not from the surge phase, recent data points, but from the appropriate phase data set. And then it gets better forecast compared to the just the BMA model. So instead of over predicting the number of cases, it learns to change the pattern over time. And we did this analysis at the county level and showed that this does, in fact, better than just the standard BMA model. Now, so this was the second part of this work was, can we identify these phases? So here, when we identify these phases, we identify it only based on the time series itself. We didn't use any other information. So now what we wanted to do is we wanted to use some auxiliary data sets. So we have a lot of extra data sets with COVID-19. So for instance, we have Google Health Trends, doctor's visits, number of tests, hospitalization, and so on. Can we utilize these data sets and get a phase prediction? So right now what we are doing is, before this, what we were doing is we were restricting the training period to the current phase. So we were restricting that the current phase, wherever we are currently, we go back and see the same phase in the past and restrict to that training period. But if we know that that our phase is going to change based on auxiliary data sets, can we update our training set here? So for that, what we use is transfer entropy technique in order to identify which of these signals are important and at what lag they are important. So we use this transfer entropy method. So transfer entropy is basically, it measures the flow of information from one variable to the other variable, or one time series to the other time series. So the definition here is the difference between the two entropies. Let's say you have a time series Y and you want to see the effect of X on Y. Then we look at the entropy of information transferred from YT with a K history to YT plus 1, and subtract the information that was transferred if we also had the information of X in the recent L data points. So this is the difference in the information if we had both X and Y, and if we only had Y. So that's a contribution that X is making in the information transfer to the next time point T plus 1. So the good thing here with the transfer entropy, with respect compared to the correlation, simple correlation, is that it can capture nonlinear relationships. And there's also a sense of directionality here. So from X to Y could be different from Y to X. But the correlation, you have the symmetric. So that's a better, that's one way to identify this directionality. And also here we identify what are the important Ks, and L are the lags. What are the Markov steps here that we need to take. And so here what we observed is that the transfer entropy to identify these leading indicators. So let's say we have this X1 to Xk, different time series. These were like doctor visits, Google Health Trends, etc. Then we want to see what is the effect of any of these Xi on Y. So we compute this transfer entropy for each of these pairs Xi and Y, identify the lags K and L with respect to Xi and Y, for which the transfer entropy is significant. So we put some thresholds that above this we had considered it to be significant, below some threshold we consider it to be not significant. And we do it, iterate it over for every week to find the leading indicators. And why do we need to iterate it every week? Is because it changed, and for every location, because it changes over because it changed over time. The set of leading indicators change over time for different locations. For instance, if you look at the Omicron period and the Delta period, here on the y-axis you have this auxiliary variables, and on the x-axis we have some states. So here we see that this is, so height of the bar you can interpret as the importance or the time transfer entropy values. They are all scaled so that they all fit in one scale, one y-axis. So here we see that for California, doctor's visit was more important, but for Florida, it didn't play as a significant variable. And it's changing over for each. And so the time period Omicron is different from Delta. So it's important to train with every new time point, and also for different locations. So once we identify these important indicators over time, we now update our Bayesian model, phase-informed Bayesian model forecast. So here we use these leading indicators and first forecast this phase at time T plus 1. So for this, we use just the empirical estimate. So we have a set of leading indicators which are important. And then we use this to identify, to get the empirical estimates for these probabilities that the phase at time t plus 1 is either going to be in surge, decline, or plateau with what probabilities respectively. Then once this phase is predicted, we update the model weights by restricting our training period to this predicted phase instead of the current phase. And then with this, we did the experiments with the bigger set of COVID-19 forecaster models, where we kept our BMA UV ensemble model. And we wanted to see whether this improved compared to our BMA and also with respect to other models or not. So if you look at the median ranking of models across different phases, so there are different, like overall, we look at Delta wave and the Omicron wave specifically. Then we look at this model ranking, so smaller the better here. And we look at this top few models, including BMA and PIBMA model. And then we see that specifically during Delta wave and Omicron wave, this PIBMA model improved in its ranking compared to BMA. And also it was better compared to several other models here. And similarly, so this was for 4 week ahead, which is a long-term forecast. And for 2 week ahead also it did pretty well compared to other models. And this work has also been highlighted in several other papers. So the first 3 papers are from our team. And the second one is the paper on the challenge of COVID-19 forecast hub, where they specify the importance of phases. And the other paper by Nick Reichbrook, where they also mention that the importance of phase can play an important role in the forecast ensemble. So to summarize the first part here, what we are trying to say is that even though you have many models which are giving you forecasts, including all the models may not be very useful. And you want to include the models which are important and with only not using the full training data set. So we want to restrict the data training period, which is more relevant. And then we made also a good contribution here was a method to identify these phases. And we introduced then the phase-informed Bayesian model averaging. And although we did analysis with the COVID-19, this methodology is agnostic to signal and can be applied to other epidemic time series as well. Okay, so I'll now cover the second part of the method, which is a non-parametric method. This is an ongoing work with a student in our lab, Nibir Mandal. So the non-parametric methods, we particularly focus on 2 types of ensemble methods. One is called the linear opinion pool, and the other is Vincent ensemble. So the linear opinion pool, so if you see this figure, you have 2 CDFs. So they don't, although we are not assuming the distribution, you can think of this as you only have some quantile information, and so you only know the CDF at certain points. You don't know it completely. Then to find this, we linearly approximate and find the CDF. Then so taking these 2 CDFs, let's say F1 and F2 from model 1 and model 2, these are the, let's say, the forecast from these some 2 models. Then the LOP, or the linear opinion pool, takes the average at any point X. It takes the average of F1X and F2X and creates the LOP ensemble. Now the Vincent ensemble, it looks at so you fix a level first on the y-axis. You fix a level and then look at what is the F inverse of X. F inverse, let's say I use Q, you fix a Q as a level. What is F1 inverse of Q, F2 inverse of Q, and then look at the average of these 2. That's and then you look at the average of these 2 here, these 2 values, and then you find this Vincent ensemble. So a quick example of this is, let's say you have 2 normal distribution, 2 random variables with normal distribution mu1 sigma 1 square, mu2 sigma 2 square. Then the Vincent ensemble is also a normal distribution. So let's say these two gray lines denote these normal distributions. Then the orange denotes a Vincent ensemble, which is all again a normal distribution with the mean being simple average. So here I'm not although it can be weighted mean, even here it can be weighted mean, here it can be weighted mean. I'm just giving an example with a simple mean. So the Vincent ensemble is again a normal distribution with this mean and this variance. And the LOP, which is a linear opinion pool, this is not a Gaussian distribution, although it has the same mean as the LOP mean. And the variance is the variance that you observe in the Vincent plus the variance within these two. So it basically so the distinction between two is that it assumes that between prediction uncertainty is similar in the sampling errors, and this need not be retained. So that and here you assume that this between prediction and uncertainty is meaningful. So how far these two models are, that's meaningful, and you need to retain that. So some related work on which, so Howard and et al., this paper, they look at this choice of so this is the reference I use for Vincent and LOP ensembles. So they look at the choice of aggregation methods in the simulated outbreak settings, and they analyze that. And they show that the effect of aggregation approach exists, there is an effect of aggregation approach on the prediction, specifically on its uncertainties. As you can see, the Vincent ensemble has a very different uncertainty than the LOP ensemble. So, and another recent paper by Ray et al., they analyzed the weighted median ensemble of the forecast, and they compare a weighted median with the unweighted median or equally weighted median. And they show that in the model development phase, the weighted median ensemble is better, where you find these weights in some by minimizing some WIS. I'll come to that. So the weighted median ensemble is better than equally weighted median, but in the evaluation phase, the opposite can happen. So it's not guaranteed that even if you find the optimal weights, it will be better in the evaluation phase. And they show that, for instance, for deaths, the optimal weights you find, they perform better, but in case of cases, that's not true. So the performance can vary in the evaluation phase based on what we are looking at. So now for the forecast, so I talked about the ensemble, simple to ensemble non-parametric techniques. Now we look at the forecast evaluation methods. So there are different forecast evaluation methods. One is simple mean absolute error, root mean square errors. But these are pretty standard metrics used in the time series, people working in the time series forecasting. So, but this mean absolute error in the RMSE, they do not consider the prediction interval or how wide the prediction interval is. They don't consider the uncertainties in the prediction interval, uncertainty in the forecast. So the other metric that was proposed was the interval score and its generalization proper interval scores. I'll cover quickly. What is an interval score? So let's say you have at some level alpha. So for simplicity, let's say 90% confidence interval. Let's say U and L be the upper and lower bounds for the confidence interval. Then the intervals for a target variable Y. So this, let's say this small y is a target variable. Then the interval score for a prediction, which is of this form, confidence interval L to U, is of this form. It looks at first the prediction interval length, how wide the interval is, and then some weighted weight by 2 by alpha, where alpha is that level. And then if the ground truth is completely missed by the interval, that's an over prediction. Then you look at how far the ground truth is from the lower bound. So that's a difference. We see how far this is from the lower bound, and how, again, in the next term, we look at how far the ground truth is from the upper bound. So by how much we miss the ground truth. So that's a interval score. That's one way of evaluating a probabilistic forecast given in terms of this confidence interval. Now, this can be generalized when you have different intervals. So let's say not just 90%, if you also have 75%, 90%, 95%, and so on, then this can be generalized to a weighted interval score. So let's say you have two intervals now at level alpha 1 and alpha 2, and you have a median. Then it basically looks at the weighted interval score, looks at the difference of the ground truth from the median. And then it looks at the interval score for each of these levels, alpha case, alpha 1 and alpha 2, and so on, whichever intervals we have. And by definition, the smaller the interval score or the weighted interval score, the better the forecast performance is. So if it covers the ground truth, it's a better score. But if the confidence, the prediction interval is larger, it's worse. Okay. So what we propose in this setup is we design a WIS-based ensemble weights, because for the forecasting community, WIS has become a standard measure to evaluate any model performance. So we'll consider, instead of simple mean or median ensemble, can we design a WIS-based ensemble weight? So we assign individual models weights such that the ensemble gets a smallest WIS score. So for that, let's say we have this time series again, Y1 to YT, and the models are again M1 to MM. Then for one step ahead forecast, which are given in the quantile format. So now again, at different levels, alpha 1, alpha 2, alpha k, and so on, we have the quantiles. Then we can compute the WIS scores for each of these models. So for this, we first propose, and also experimented with this loss function, where we minimize this square, so we look at this expected WIS score from model MI. And then we look at the square weight here, such that these weights are basically the total sum is 1. That weight, this is the weight we are going to assign to individual models. So this is our target loss function. This is something we want to minimize. Now, there's a solution here to this loss function, a very clear, clean solution we have, which is that the WI weights, which are inversely proportional to these expectations, will minimize that loss function. But the problem for us is that we don't know that for the forecast time point t or t+1, when we have not seen the ground truth, we don't have the actual ground expectations. So for that, what we do is we go back and take a time training period t, and then look at the individual model WIS scores over that training period t, and look at the average. So we assume that the performance of a model in the training period would be similar in the evaluation period. And once we have this approximation, we can find these weights here. Now, based on these weights, we did the experiments, and how this method is important is design with this WIS-based method. This, again, we make it adaptive, that we train it over time. At every time point, we update our model weights and look at the WIS-based ensemble. And it is much simpler if we compare it with the BMA, where we were obtaining these model weights based on the historic data points again. But there we had to implement the EM algorithm, where to find the optimal weights at every point, we need to run an optimization algorithm. And here we have a solution. We know what the solution is, what are the optimal weights here. And for this particular proposed approach, we experimented with the COVID-19 case count time series with our internal set of models. And we compare it with the other ensemble methods here. And we also did LOP and Vincent both ensembles. So the experiment setup was of this form. So we look at this 1 to 4 week ahead, called the horizon 1 to 4 week ahead forecast. And the timeline we considered was August 2020 to December 2021. And we looked at all the counties within US, and I'll show some results for US or New York State. And the training point, so because we observed that the model performance has been changing over time, I'll show one heat map here. We only look at the recent 4 weeks to train for the training period. And then once we have the appropriate weights, we look at both LOP, linear opinion pool, and the Vincent type ensemble. And then we also compare it with BMA, mean ensemble, and the median ensemble, which are some of the standard ensemble models. And different quantized level for the forecast used were these different quantile levels. So if we first do a retrospective analysis of how these models performed over time. So we had this internal set of models. Over time, if we see that if we rank all these models by their performance for 1 week ahead, short-term forecast, or 4 week ahead, long-term forecast, we see that this model, so here, this is a rank plot. So the smaller or the darker color means a better performing model. So there are some models which are performing better compared to other models like ARIMA or Airspatial with respect to other models. But there are also some other models like Kalman filter, which were performing really good, and then suddenly their performance drops. And like LSTM, it was not doing well, and then suddenly started doing well, and so on. So that does highlight the importance of retraining at every point and assigning these model weights, updating the model weights over time. So we compute this, we evaluate our WIS. So we use this proposed WIS based ensemble approach. And then we compare the WIS of from these two different ensembles that we get from with using the optimal weights, and compare with mean ensemble, median ensemble, and the BMA. So here the dotted line represents the weekly case counts for the US. And the red is the LOP ensemble. The yellow one here is the BMA ensemble, and the other green is the mean ensemble, and so on. So here we clearly see that the red one is mostly below the BMA ensemble. So it definitely does better than the BMA. So there is no need to implement a much complicated EM algorithm setup, algorithm to find optimal weights. We can do better by a simple method. But it's also important to highlight that the mean ensemble is also doing pretty well comparatively to every other model. So mean, median, and this WS-based ensemble were very close to each other over time. So the earlier figure was for 1 week ahead, and this is for 4 week ahead. Again, here on the y-axis, we have the WI scores. And these are much larger than the 1 week ahead forecast, because these are long-term 4 week ahead forecast would have a wider uncertainty usually. So that would have a bigger WI scores. Here again, we observe that this red, which is the LOP ensemble from the WIS-based ensemble, does better than the other two or three ensembles. And I'll quickly cover the last few slides and some work in progress. So we then compared, similar to our BMA, where we compared the Omicron and Delta waves differently. Here again, we compare the phase-specific performance and based on the model rankings. So we look at the rankings based on the WIS scores of individual models. So here on the x-axis, you see the model rankings for 1 week ahead, short terms and long-term forecast. Again, we see that this, so here the bar height denotes the percentage of which the specific model was ranked number 1. The number of times that the percentage, model was ranked rank 2, and so on. So here again, we see that the WS ensemble did get higher weightage compared to the other BMA, for instance, over time. Okay, so the other thing that we wanted to capture with this is that can we mitigate the worst case scenario? Can we actually find the best performing model? So with this optimization, did we actually find the best performing model over time or not? So for that, so basically, let's say this blue region, this is the area covered by different lowest to the highest WI score from the individual models. Can we capture this lowest WI score? So whichever model this is, the model could be changing over time, the best performing model. Can we capture this over time? So that we showed that we can with the LOP and the Vincent. And in fact, we can do better in some places. So this can even be better than the individual models in some places. So for this, we also use this metric called performance gap, where we look at this reference model, which is the model WS score, which is the minimum among all the models. And we look at this performance, we define this performance gap metric as the difference or the ratio or this percent change from this reference model of for the ensemble model. So we look at the ensemble model and how far this is from the reference model, and then we scale it appropriately. And we keep it a sign difference to see whether it goes in the upward direction or the downward direction. So here again, from this figure, we see that the LOP ensemble does better as the number of the performance gap is much smaller in some cases it is higher. Okay, so I'll quickly cover some ongoing work here. So our next target is to improve this. Can we improve this performance gap? So here we see that this performance gap was not really improved by this method, and there is a scope of improving that. So one of the challenges that we saw here is that when you're forecasting in time for time t+1 to t+4, we need optimal weights for these 4 time points. And when we need weights for these 4 time points, we are approximating based on some training period. Now this heat map shows the optimal weights over time. So whatever the optimal weights we obtained till in the training period, if we use these optimal weights for the future, that may not be a very good approximation because they are actually changing over time very rapidly. So is there a way that we can do better than this approximation? So what we propose here is that instead of just minimizing the WIs of the ensemble model, we add this regularizer term here, lambda times norm of W. And one more point here, I forgot to mention that this heat map shows the optimal weights, and the optimal weights, there can be more than one optimal weights. But if we find this and some optimal weights which are very sparse, like it can change from 1 to 0 over time, then the approximation may not work very well. Now, if we add this regularizer term, what happens is that now this sparse weight would become more uniform over time. And why is that? Because if adding this term in the loss function means that we are penalizing more for sparse weights. So if the weights are sparse, this norm W2 would be much larger. And so with this, so we are basically trying to find the optimal weights in the neighborhood of uniform weights. And if we can find some optimal weights that exist within the neighborhood of optimal weights, that would be a better approximation for the future time point as compared to the sparse weight. So I'll summarize, and if there are questions, I can take that. I hope we have a few minutes for that. So I talked about the phase-informed BMA and different ensemble techniques, and also the WIS-based ensemble. And the future direction, we are looking at how can we improve this performance gap? Can we increase our lower bound so that we can decrease, or can we increase our reference WIS score a little bit and make sure that we actually come near the reference WIS scores? And we also want to explore, although we are doing this for COVID-19, we want to explore this for influenza and other diseases. Thank you so much. If there are any questions, please.
So questions from the audience, please feel free to put anything to the chat or the Q&A, or just raise your hand. I think we can take that. I'm getting some applause here. Thank you. Let me start things off. I just want to start with a real question here. That maybe I was just missing it from your nomenclature, but did you compare the Bayesian phased ensembles to the WIS ensembles, or was it just the original non-phased ensemble that you were comparing?
Yes, we were comparing with the non-phased one.
So you don't really know if the phased beats out the WIS. Was there some reason why you didn't do that comparison?
We are yet to do that. This is
Okay.
like ongoing work, so this is not yet. Yeah.
No,
So
that's fine. That's fine.
yeah. 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 So we should have included the phase informed ensemble here too.
Okay, so let me then ask, since we don't have other questions, I'll throw some other, a couple other things that came to mind here. So your phase segmentation, sort of based on this 10% change, that seems a little arbitrary. And
Yeah.
I'm wondering about that, particularly in the case of what we have seen with some of this data being fairly noisy data that, have you looked
So
at other values of the threshold or thought about ways to handle a lot of noise so that the 1 day of high reporting doesn't necessarily
yes, so
trigger
we
the
did
threshold?
look at this different thresholds here. So we looked at different like plus minus
Mhm.
2 and 3 here, like 7 to 12% and so on.
Mhm.
And what we see that if you go at the county level, the time series is much more noisier.
Right.
At the state level, the time series is better or it's much smoother than the county level. So what we did is we did this phase classification at the state level.
Mhm.
And at the state level, this 10%, if you make it plus minus 1 or plus minus, so it did not change much except 1 or 2 points near the plateau phase.
Mhm. Mhm.
So because when you see that there is a surge, it's actually much more, usually much more than 10%.
Mhm. Mhm.
So when it's closer to 10% and if it changes when you make it 10 to 11 or 10 to 9,
Yeah.
it's mostly near that plateau phase that we are defining.
But
So
sorry, go ahead, finish up.
yeah, so I was just saying that it mostly changes if we change these numbers, then the maximum change you would see is near those plateau regions. And most of these regions, you'll see very small plateau regions here.
Mhm.
And the other thing, if to avoid that noisiness in the time series, we did this phase classification at the state level, and then populated that at counties within that state.
Mhm. Mhm. I see. Got it. So you use the phase identified for the state to
Yes.
inform the models for each county. Okay, got it.
Because for counties, we found that this fit doesn't really capture because sometimes the time series is really noisy and you cannot really fit.
And is this based off of raw data as reported by the
Yes.
states? Okay, got it.
Yeah.
So did you have to deal with any of the reporting anomalies to handle that? Because what I'm thinking is those times when the states dump a bunch of I guess it's mostly with deaths they do this, when they dump a bunch of deaths, then you could get something that looks like a false surge.
Yes. So for state level, we didn't really see such anomalies. And mostly they are usually back if there are some errors, they get corrected in next few weeks. So when we take time series at any given, and we also did it as of that time t. So when we are doing this phase informed Bayesian model averaging, so for any time t, whatever that time series available at that time,
Yeah.
we did the phase classification on that.
Okay. Well, I've got a couple of other questions I can ask, but I want to give a breath here to make sure anybody in the audience can fire away with questions if they have anything. Okay, so hearing nothing, I'll just keep going. What about incorporating the phase information with the WIS? Would that make sense? Or would that
Yes,
be a silly thing to do? Or have you thought about that?
Yeah, so for that, we first need to see whether, yes, but that's a good idea though. So here we don't know whether the small rankings, yes, actually that might make sense. This WS based on, so we take the training data only with a phase specific training data, yes.
Yeah, I'm thinking of just in a sense of saying, your inclusion of the phase data sort of is based on the hypothesis that understanding the overall trend is an important piece of information to improve the ensemble. And it seems like that could work equally well for the parametric and non-parametric. Or at least if it works one, it might work for the other. And so comparing those things to sort of understand when the phase information helps would be an interesting question to look at.
Yeah.
And so another question that comes to mind here is, I'm sort of fascinated by this notion here of, okay, wait, there is a question here from the audience, so let me defer to that. Okay, so I'll read this here. Did the data used to train these models include backfilled counts? If so, how would the performance change if the models were trained prospectively rather than retrospectively, which would not have included those backfilled values?
So we did use the unbackfilled version. So for the BMA ensemble work that we showed, this one, results we showed here. So this was used with the unbackfilled. So as of whenever we are forecasting, we are using the same data that was available to any of the forecasters or models there. But so it would not be a fair comparison if we use the unbackfilled version for our ensemble technique, because that's not the same data individual models are receiving. So one model could be taking care of the backfill, like this will go into the backfill, and then that would get a better weight if you look at the cleaned up version or the backfill version. But if you don't look at the cleaned up version, you only have what is available at that time, then that model would not get a very good weight, may not get. So although we did not compare it, what that difference would be, but I think the second one would not be very fair. It's like comparing two different things, but yes, we didn't compare these two.
Okay. All right, we've got a couple more questions that have come in. It is just about the top of the hour, so I hope you have a couple more minutes to answer questions.
Yes, of
Thanks.
course.
Okay, and of course, if anybody needs to leave, no offense taken. Here's another question here. Can the individual model uncertainties be incorporated in any of the proposed ensemble mechanisms in a way that the prediction uncertainty gets minimized?
That's what we are doing in the WIS ensemble, right? That individual model uncertainties we are incorporating so that the ensemble uncertainty is minimized.
Okay.
Yeah.
All right. Another question here. Have you tried using a probabilistic model for phase rather than using a single phase at test and prediction time? So I guess that's sort of a generalization of my question about the cut points. A probabilistic model might be another way to look at that.
So we actually did try to make it probabilistic, that we assign probability that we make it 10%, and if it is within some delta neighborhood of 10%, then we assign it in surge, decline, or plateau with some probabilities. So
no, I think that the probabilistic question there is more rather to say not the rate of change, but at any given point coming up with an estimate of the probability that it is a surge or a plateau or a decrease.
So you mean not through this just strict like thresholds like 10%?
Exactly.
That can be done. But what we so the one point here that I would like to mention, that we evaluated how good this linear pace. So if you see there are two lines here. One is the blue with the blue dots and one with the straight bold black line. And it's approximate. So we find this optimal breakpoints in such a way that this distance between the two is minimized, right? And this linear piece fit we find is much better. So this difference between the two time series, the approximated and the actual time series, it's actually very small in several cases. We are doing it at state level, where the numbers are pretty high. If you see on the y-axis, these are pretty high numbers, but the difference between the two is much smaller. So that ensures that we have a very good approximation. Now from here, yes, we can, after doing this, if there could be some probabilistic way of finding these phases, but I'm not sure like what the other methods could be here once you have this good fit. Now we found that, so we did explore several methods here, and we found that this is one of the simplest method that captures. And if you see this figure, like we plotted this and we found and also compared all these numbers, that this way of finding these different phases is pretty robust, and it works really well compared to other methods.
Okay,
and
great.
it also keeps the trend in the time series. So if you look at, if you approximate or smooth the time series with, let's say, some moving average of window 3 or 4, then it smooths out the time series. We don't want it to be smoothed out. We want to keep these trends, like if there is an increase or decrease trend, sudden increase or decrease trend. So that moving average also didn't work. So yeah, but yes, there could be some probabilistic methods of finding these phases.
Okay, so the final question I think we'll take for now. WIS is strongly correlated with the scale of the outcome. Bosie et al. Suggested using the log of the observation and the log of the forecast before calculating WIS. Do you think that might improve the weighting?
So instead of WIS, we did look at the relative WIS. So here instead, when we minimize the WIS scores, we actually minimize the relative WIS, where we scale it by the ground truth. So that scaling issue is then gone.
Okay. All right. Well, there are no other questions, and we're a few minutes past the hour, so I think it's a good time to wrap up. Thank you, Dr. Kaur, for your speech, your talk, and nice work and interesting discussion afterwards. So thank you, and we will see you all in May for our next webinar.
Thank you so much. Yeah.
Thank you.